All right, now let's go ahead and take a look at example 4. Notice that this example here is just asking us to evaluate a double integral over a specified region D, which is a region in the first quadrant bounded by the graphs of y equals x squared, x equals 0, and y equals 4. Now, I'm actually not going to start doing this question immediately. I actually would like you to pause the video really quick and see if you can go and take all of the knowledge that we've learned so far in this section to figure out the best way to maybe try to tackle this question. So go ahead, pause the video, see how much of this you can fill out, and then when you unpause the video, you'll see me go through the solution. Okay, so hopefully you actually gave this problem a chance. Let's see exactly how I would go through and do this question. So the first thing that I'd be interested in is what does this region D look like? Okay, so I'll say here that we will create a picture of D. All right, so I know that D here is going to be over in the first quadrant, and I'm only then going to really be worried about sketching this portion of y equals x squared. I'm interested in x equals 0 as another kind of bound on this region, and that's going to be my y-axis. And then I also have up here at y equals 4. So I have ultimately this region kind of right in here. This is my region of D that I'm working with. And so I'll just go ahead, mark that. There's my region D. So I'm going to be interested in trying to define what this region D is. Remember, we talked about that defining our region is going to be super crucial. So I'll say here that we define D to be equal to collection of points x comma y. And again, I can kind of see this region as either a region with a top curve and a bottom curve, or as a left curve and a right curve. For the moment, I'm guessing that maybe most of us saw this as a region with a top and a bottom rather than a left or a right, but I'll go ahead and kind of write both different possible descriptions of D here. So if I'm going to see this as a surface with a top bound and a bottom bound, that bottom bound would just be the surface of, or sorry, the curve of x squared, and the top would be at 4. You could have also gone ahead and expressed this as a left and right bounded region, but in that case, you would see that x is bounded by 0, and on its left side it would be bounded by root y, which is exactly what I would get up here if I had rewritten this to be x equals and only considered the positive half where x's were actually positive. Of course, if I have this, then this means that y is going to be kind of freely varying between 0 and 4. So it wouldn't matter which one of these, again, that you chose. I'm going to go ahead here and consider kind of what both of these would look like as I set this up. So I'll say that my double integral over d of x e to the y squared dA is either going to look like, if I used my first description of d, it's either going to be going from x squared to 4 and then 0 to 2, x e to the y squared, and then this would be dy dx, or I could have expressed this as using the other integral going from 0 to root y and then 0 to 4, x e to the y squared dx dy. Now again, both of the setups are perfectly fine, but as we've seen in some of the previous problems in this section, the order in which I choose to set up my differentials might have some implications as to how difficult the resulting integral is. Now, it's entirely possible that you could try the integral in both ways, but I would actually think that this integral over here is going to be extremely difficult to actually go through and do, because it's going to require that I integrate first this e to the y squared. And that is actually going to be impossible for us to go ahead and accomplish. So it actually turns out here that we need this second description of d in order to proceed. So I'm going to go ahead and proceed here off of this second integral that we have. And if you went ahead and started to integrate here, let's see what we would come up with. We'd have a 1/2 x squared e to the y squared, because again, I'm just integrating here with respect to x. And when I do this, I'm going to end up with a 1/2, it looks like y, after I square the y squared, and then an e to the y squared dy. And this is now great because now I'm not just integrating an e to the y squared, I also have this extra y sitting out front. And this allows me to perfectly set up a u sub. So I'm going to go ahead here and I'll let u be equal to y squared. And then that would mean that my du is going to be equal to, let's see, a 2y dy. Or I could rewrite that as a half of a du is equal to a y dy. So this would allow me to go ahead and complete a nice substitution here. I think if I did this, I'd have a 1/4, one from the 1/2 here, and another 1/2 from the du substitution that's coming. And then I'd have e to the power of u and du. Don't forget, though, that when you're doing a substitution, we always need to change our bounds. And so in this case, I'd say that my lower bound where y was 0 is now going to turn into, well, I guess it's still just going to be a lower bound of 0. And my other bound of 4 is going to turn into 4 squared, which would be 16. So I should have new bounds here of 0 and 16. And so then I can easily integrate this. This is just going to be 1/4 e to the u, and I evaluate that from 0 to 16. If you didn't use a u sub here and you were just kind of able to do that in your head, that's totally fine. There's nothing wrong with that. In fact, that'll probably be faster in a lot of instances. And you can see here I've gotten all the way down to my final answer. I have 1/4 times the quantity, e to the 16th power, minus 1. So hopefully you were able to get something like this, or if you were ultimately getting stuck, hopefully you might be able to see where you went wrong. Of course, if you have any questions about an example like this, always feel free to reach out to me and let me know.